Our next speaker, our invited speaker, is Edward Lee, and I'm sure all of you know him, but I'm going to say a few words. So Edward worked on embedded software systems for 40 years, and he got his BSc from Yale, master's from MIT. He worked at Bell Labs, then he got his PhD at Berkeley, and he stayed there. And now he's a professor of graduate school in the EECS department of Berkeley. He has been working on cyber-physical systems. He's a pioneer. His papers on cyber-physical systems are many citations. And now he's also working on other books. So he had many textbooks, but now he's writing books on philosophical and social implications of technology. There are two books that he has, The Plato and the Nerd and Coevolution, if you want to have a look at those. So I'm not going to take too much time from you. And Edward, please start.
Thank you, Marjan. I appreciate the introduction, and I appreciate the invitation to talk to ASYDE. I'd never been to this workshop. I guess it only happened once before. Is that correct? And so I feel like I missed it. And these first two talks, the second one I had a little trouble following the audio, but I think it seemed like it, as well as the first one, are very good lead-ins to what I'm going to be talking about. So what I'm going to talk about is more deterministic software for cyber-physical systems. And in particular, I'm going to try to motivate a project that is really the central focus of my research group right now. And it's a collaborative project, actually, with several people around the world, most of them in either Berkeley or Germany. And I've listed on this page here the key people involved in this software development. And so I really give them a lot of credit for what I'm going to be talking about. Let me begin by motivating the problem just with the context of cyber-physical systems. So as Marjan mentioned, I work in cyber-physical systems, and here's sort of a cartoon of what I mean by that. It's a system that intrinsically involves some physical plant, typically more than one computational platform. These are the embedded processors or sometimes cloud-based services, and some kind of network fabric that communicates, mediates the communication between these computational platforms. And the major challenge here is integrating these rather complex systems and in modeling and understanding the integrated behavior of the combination of software and hardware. I'd like to just begin by giving an astonishingly simple challenge problem. And I think the first speaker today gave more interesting applications that actually have very similar properties. But this is a surprisingly simple problem that has no real good solution today. So suppose that you want to automate the opening of an aircraft door. So this is something that is done manually today. So a flight attendant looks out the window, sees that the ramp is adjacent to the door, and then disarms the door to prevent deployment of the escape slides. And then that changes the color of a flag that is visible from outside the aircraft. And then the person on the outside of the aircraft opens the door. So suppose we want to automate this, and we're going to put into the door a microprocessor that is on the network on the airplane. And it's going to provide two services. We'll simplify this. We're not going to worry about closing the door or anything like that. So the two services are open the door and disarm the door. Now, assume that the state of the door is closed and armed. My question is very simple. What should your software do when it receives a message to open? Okay? Now, this is an astonishingly deceptively simple question, right? Because it seems like the obvious answer is if it receives a message to open the door, it should just open the door. But that can be disastrous. If you open the door when it's armed and it's adjacent to a ramp, it becomes a safety critical situation where the escape slide deploys inappropriately and people can get seriously hurt. So it's not so obvious that you should just open the door. So let's think about what a possible architecture might look like for the system. So we've got this door controller on the right that's sitting in a microprocessor in the door, and it's able to receive disarm messages and open messages from the network. And we have a number of other subsystems. So we have an embedded vision system, for example, that is verifying that there is a ramp adjacent to the door or there is not a ramp adjacent to the door. And when there's a ramp adjacent to the door, it will issue a disarm message. And this might be something that would be implemented manually today, but we could automate it, right? Then there's the cockpit control, where the pilot can issue both disarm and open messages. And there's a fire detection system that when there's an emergency on the aircraft, it simply issues an open message, and it wants the door to open whether it's armed or not. Okay? Now, for the communication here, there's any number of schema that we might use. We might use publish and subscribe, as done, for example, in ROS, which is very commonly used in robotic systems, and this is arguably a robotic system, and therefore ROS might seem like a natural a platform to build on. Or MQTT, which is used in IoT applications, and there's a number of other publish and subscribe fabrics that are pretty common these days. We might use a message passing service like UMLRT, which the first speaker was talking about today, or the actor-based frameworks in Agha or Erlang or Ray. We might use a service-oriented architecture, which is essentially a remote procedure call. One of the popular implementations of that is Google's gRPC these days. Thrift is another one. Or we might use some kind of a shared memory abstraction. So these are a number of solutions that are used for communicating between software components today, and often, in fact, used in applications not too dissimilar to that. So the question remains, what should the door controller do when it receives an open door message? Well, one option is just open the door, but how much should you test this? How much formal verification? How to constrain the design of the other components, the network? I mean, the obvious problem is that one of the components could have issued a disarm message, and these messages arrived at the door controller out of order, and the open message arrives before the disarm message. So somehow you're going to have to constrain the network design in order to prevent that kind of scenario from happening where the order of messages gets reversed. You could try to develop a distributed consensus. So you send out an OK to open message with a warning that the door is armed, and you wait for responses. But how many responses should you wait for? How long should you wait? What if a component has failed and never responds? Remember that the fire detection system wants the door to open whether it's armed or not, so components may have failed. And the real problem here is that the software developer is going to have to go and read all of Leslie Lamport's papers, and many of which are impossibility proofs about the ability to develop such a distributed consensus in the face of a certain number of failures. So this is going to make the software development problem extremely challenging for an extremely simple scenario, which is a really problematic scenario. Now, another possibility is we could just wait a while and then open, okay, on the assumption that if a disarm message has been launched into the network, it will eventually get to us. But now the question is, how long should we wait, and how are we going to justify that decision about how long we wait to a certification body like the FAA, which certifies avionics software? So it looks here like there really isn't an obviously good solution to this. So maybe we could fix the problem with formal verification. So we try to analyze the system and we look for certain properties. So one property that we could easily express in linear temporal logic, for example, is if a door receives open, it will eventually open the door, even if all other components fail. That seems like a reasonable property. The second one is if any component sends disarm before any other component sends open, then the door will be disarmed before it's open. Again, this is something that we could express very easily in LTL. But these two requirements are actually both very problematic, and arguably they actually don't make any sense. So the first one is problematic because of the requirement that this should eventually open the door even if all other components fail. So that makes developing a distributed consensus extremely challenging. But the more fundamental problem is this word before, okay? Because this is a distributed system and it requires comparing times of events in distributed platforms without specifying a model of time. Now, you might think, well, okay, we'll just naively use a Newtonian model of time. But the Newtonian model of time is not actually accessible to any physical realization of a system. And in fact, we now know from the theory of relativity that in physics, the order of separated events depends on the observer. So the word before here is actually not a sound basis for building a formal requirement for the system until we introduce into the system some kind of a model of time, and we have to make that model of time very explicit, and then we have to figure out how to make the system conform with sufficient reliability with that model of time. We can't just rely on the background physics notion of time because that word before makes no sense in the background physics. So let's zero in on one of the families of popular techniques. So this is one very closely related to the one that the first speaker was speaking about. It's used in UMLRT, where you have messages that are sent asynchronously, and you have a message queue that handles those messages in, first out order. So there's many popular frameworks that are using this kind of mechanism today. So the foundation for these dates back to the 1970s in Carl Hewitt and Agha's actor model, where you have a message queue that can receive messages from any number of other sources, and then those messages are handled by message handlers in order of arrival. Okay, that's the basic Hewitt actor model. So if you have just two actors, a source that sends disarm followed by open door, okay, so the handler here, so this is a syntax that is very similar to the way it would be written in Ray, which is one of the popular actor-oriented frameworks. The handler main creates a new door, it sends it a disarm message and sends it an open door message. Now, suppose that there's a TCP socket communication between that source actor and the door handler. In that case, we can rely on properties of TCP sockets, which is that they deliver messages in order and reliably. Okay, eventually. They provide no real-time guarantees, but the TCP protocol is about delivering messages in order and reliably. And relying on that property of TCP, you could be, in fact, assured that the disarm handler will be invoked before the open door handler. But this is a rather simple architecture, much simpler than the architecture that I showed you before, where we might have an embedded vision system that can also send disarm messages and a fire detection system that can send open messages. So in particular, if I just elaborate this actor model with an intermediary actor, say when the disarm message gets sent, it is passed through an actor that consults with the vision system to determine whether there is a ramp adjacent to the door, to determine whether it is in fact safe to disarm the door. Okay, so let's call that actor pass disarm. And the code that I've written here is rather trivially simple. There's no embedded vision system. It just forwards the message. Okay, so it's as close as you can get in a message passing system to a no-op. It doesn't do anything but forward the message to the door. Now, in this situation, there are no reasonable assumptions about the network that are sufficient to guarantee that disarm will be invoked before open door. TCP sockets will not do the job because there might be a TCP socket between source and pass disarm, another one between pass disarm and door, and a third one between source and door. And there's no assurance about the order of delivery of messages across TCP sockets. It's only within a given socket. So, in fact, all of the frameworks that I described before, the publish and subscribe, all of the actor frameworks, all of the service-oriented architectures, which do remote procedure calls, and all of the shared memory fabrics have this property that as soon as you've got this more complex communication, there is no semantics to the relative order of delivery or handling of messages. And as a consequence, you can't provide any assurance about the ordering of the message handlers here. So, some possible solutions. Probably the most common one that engineers would use is simply to ignore the problem. But in my view, that's not acceptable. We could try to model the timing in the system and model the timing in the network. And in fact, in an avionics context, this is actually probably a practical thing to do because the networks are real-time networks. They're not your usual Ethernet with TCP/IP flowing over it. And so modeling the timing might really be possible in that context. Also in the automotive context, in using networks like FlexRay or some time-sensitive Ethernet network, it might be possible to model the timing. But this is going to be a pretty serious modeling problem, and providing assurance of the ordering here is going to be quite challenging, even for such a simple application. So the alternative that I would like to advocate is actually to change the model of computation. And there's any number of models of computation that you can use that will give you deterministic behavior across distributed systems, and that will, in fact, provide global guarantees on message ordering. Data flow models will do this. Process network models will do this. Synchronous reactive programming languages will do this. And my favorite, because it's the one on which we base our language, is discrete events. And so this is the one that I would like to focus on. So in the discrete event solution, the way that the program is expressed and the semantics of the framework that executes it is changed in a very fundamental way, which is that every message logically has a timestamp. And these timestamps define the order in which messages get handled. So if the open message has timestamp T2 and the embedded fission systems message has timestamp T1, the order in which these messages is handled at the door controller will be determined by the numerical order of these timestamps and not by the order in which they arrive. So how can this work? I mean, that seems like magic, right? Because the embedded vision system has to somehow assign a timestamp to this message, and it is a separate microcontroller on the network from the fire detection system, which also has to assign a timestamp. And then we have to somehow compare these timestamps that are separately assigned throughout the network. That's an implementation challenge, but now we have a really significant advantage from a perspective of semantics and verification, which is that we have a well-defined definition of what it means to correctly execute the program. The door controller will be correct if it handles messages in timestamp order. So discrete event models have been around for a long time, and they've mostly been used for simulation. And here we're actually proposing to use them not for simulation of systems, but rather for deployment of systems in a cyber-physical context. So you can go to, hardware description languages are based on this kind of discrete event formalism where all of the events are timestamped and events are handled in timestamp order. There's been a lot of work historically on distributed discrete event systems as well, and I'll reflect on this. So in particular, let me focus on this question of distributed systems and how we implement this with distributed systems. Now, I'd like to give you an existence proof that this can be done, and it can be done at very large scales and very efficiently. And that existence proof is Google Spanner, which is a globally distributed database that was first described in a paper in 2011 by Google. And the way that it works is it connects a distributed database that is scattered across data centers that are all over the world. So this particular map shows a bunch of the data of Google's data centers in the US. And these data centers have replicated data. So each data center can handle queries coming into the data center and will issue responses. So this might be used, for example, for an airline reservation system. So you could have a scenario, for example, where a query comes into Seattle to reserve a particular airline seat. So that wants to change the state of the database to mark this seat as reserved. So the Seattle data center will assign a timestamp T to that query. Now, suppose that around that same time, a query comes into the Dallas data center asking if that airline seat is available. That data center will assign a timestamp R, and now the definition of the correct behavior of the database system is based on the numerical order of these two timestamps. Okay? So if T is less than R, then Dallas should respond that the seat is not available. If T is greater than R, then Dallas should respond that the seat is available. All right? So how do you implement this? Because one query came into Seattle, one query came into Dallas, and is there a way to do this efficiently? Do we have to actually develop a distributed consensus for every query that comes into every data center around the world? Well, that would not scale. So that's clearly not what Google Spanner does. So what does Google Spanner do? Well, let's look at some possibilities, right? So here's a simplified view of what the architecture looks like. So you have one data center that is located in Dallas. No, Seattle. This is the Seattle data center. So it's running a web server, and the web server receives a query to reserve the seat. Okay, and it wants to then update the database, so it sends a message to the database actor to update the record to indicate that this seat is now reserved. Now, since this is an update to the database, that update needs to be broadcast to all the other data centers because they have replicated the data in the database. So that database is going to send out a message that's going to be received by every other data center saying, and that message says, I would like to change this record so that the airline seat is reserved. And now the database system has to be notified of this update. Now, suppose that around that same time, the web server in Dallas receives a query with timestamp, assigns it a timestamp R, and it wants to know whether that airline seat is available. So now we have a situation in Dallas that this is all we know. Okay, locally, we'd have no idea what is happening in Seattle. All right, the platform in Dallas, all it knows is that it has a query asking if the airline seat is available. So the question is, how should it respond to this query? It's got timestamp R, but it has to somehow be sure that it isn't later going to see a message updating that record with an earlier timestamp. So there's a number of ways that we could solve this. A classical approach is called the Chandy and Misra approach, which is used in distributed discrete event simulation. And this dates back to 1979. And this assumes that along every message channel, events arrive reliably in timestamp order. This is not a global property. This is on each connection between a message sender and a message receiver. So this is practical because we can implement this using TCP/IP. So what the Chandy and Misra approach does is when the database has a message with timestamp R, it cannot respond to it until it also has a message on its other update port with some timestamp. Okay? It has to wait for that message, and then once it gets that message, it can just compare the numerical value of these two timestamps and respond that the airline seat is available, for example, if R1 is in fact less than T1. The problem with this is rather obvious, however, which is that the updates to the database may be rather infrequent, and so these messages coming into the update port of the database may be infrequent, and as a consequence, the database may have to wait quite a long time before it responds to this query about whether the seat is available. And that's not going to be very useful for any kind of cyber-physical system or any kind of system that has an interaction with the outside world. You can do this for simulation, but you can't do this for a real-world deployment because you want to know now whether the airline seat is available, and human response time is on the order of 30 milliseconds. So we want to respond, the database should respond within 30 milliseconds. So Chandy and Misra have a solution to that, which is that if you want the database to respond every 30 milliseconds, or within 30 milliseconds, then this database here should send a message at least as often as every 30 milliseconds saying, I have nothing to say. I have no updates for you. I have no updates for you. It just repeatedly sends those messages. I have no updates. So these are called null messages, and they create an enormous amount of network traffic in a distributed system and a lot of overhead in the processing. So this isn't really a terribly attractive approach for a real deployment. It also, more seriously for cyber-physical systems, it makes every single component in the system a single point of failure. If any one database goes down, loses its network connectivity, it'll stop sending messages, and all other database components will stop responding because they're waiting for messages from that single component. So that's a disastrous design for a cyber-physical system. So there's another possible approach, which is due to Jefferson, published in 1985. He called it time warp. It's more commonly called optimistic computation, which is where the database component in Dallas, when it receives a query R, it will simply speculatively respond. Yeah, as far as I know, the airline seat's available. And then if it later receives a message with an earlier timestamp, it backtracks. Now, the problem with that is also obvious, which is that you can't really backtrack an interaction with the physical world. So if the web server has already responded that the airline seat is available, you don't want your web page to have to say, oops, I was wrong about that. Sorry, I need to take it back and pretend I never said that the airline seat was available, right? So, in a case of just an informational service like an airline seat reservation, it's not disastrous. But if you're driving a physical actuator that is opening the aircraft door, for example, and the slides have already deployed, then retracting the message saying, oops, I didn't mean to open the door isn't going to help much. So this is not really a solution either. It does have the property, however, that there is no single point of failure, because if any one component goes down, it just simply stops sending messages and you won't be able to backtrack. This solution also has considerable overhead, actually, because you have to snapshot the state of the system periodically. And then when you have to backtrack, you have to roll back to the state of the earlier state of the system and then process all the messages that you've received since then in timestamp order, which leads to uncontrollable latencies, which is not, again, going to be very good for cyber-physical systems. It's probably okay for simulation, but not for any kind of deployment. There's a third approach that was largely developed in the 1990s and early 2000s and is still in use, which is to provide a centralized controller that's called the runtime infrastructure. And every component now will maintain a local notion of logical time, and it will consult with the runtime infrastructure. So if the database component in Dallas wants to process a message with timestamp R, it makes a request of the runtime infrastructure, asking the runtime infrastructure, can I update my local notion of logical time to R? And the runtime infrastructure will wait for messages from the other components in the system, and only when it receives those, it will issue a time advance grant to each of the components, allowing them to advance their notion of logical time. And at that point, the database can reply. But you still have a single point of failure. Actually, every component is still a single point of failure. And again, so this works for simulation, but not for online processing. So this is not what Spanner does. What Spanner does is really much simpler. So the database component in Dallas has this message with timestamp R. What Dallas does is it just watches its local clock. And when its local clock exceeds this threshold, R plus W plus L plus E, it responds that the seat's available. Now, where does this threshold come from? Well, I can explain that. So first, there's a local clock on each platform, and that's used to assign the timestamps. So T and R are drawn from local clocks. So when the web server receives a query, it consults its local clock and uses that timestamp as the logical time of that message. It assumes a bounded execution time, that the database will send out its update message within a bounded amount of time. It assumes a bound on the network latency, L. With those two bounds, Dallas will know about the message with timestamp T when the clock in Seattle reaches T plus W plus L. But Dallas doesn't have access to the clock in Seattle. So Dallas has to add an additional assumption, which is that there is a bound on the clock synchronization error, that these two local clocks in Dallas and Seattle do not differ by more than some bound. And at that point, Dallas can be assured that the event will be known in Dallas when the Dallas clock exceeds the threshold T plus W plus L plus E. So that's where this threshold comes from, and it leads to this, what is called a safe to process threshold. And of course, there are assumptions here: bounds on execution times, bounds on network latency, bounds on clock synchronization error. Most of these assumptions, I mean, the bound on network latency is a universal assumption in distributed real-time systems, right? If there is no bound on network latency, that's equivalent to having an unreliable network that where the messages will potentially never arrive. And so if you want to assure correct behavior, you have to assume some kind of bound on network latency. Similarly, assuming bounds on execution time is pretty common. Assuming bounds on clock synchronization error is new to this framework. This approach, however, has really nice properties. There is no single point of failure. Any component can drop out of the system and all other components continue operating. Moreover, a component can process events with no network traffic. There doesn't have to be a distributed consensus with a whole bunch of messages sent. There's no null messages. So the additional load on the network for infrastructure work is negligible. It's actually the only additional load on the network is for clock synchronization, which is very modest. The latencies now are well defined. Because you have this safe to process threshold, you can actually specify a requirement that the database needs to respond within 30 milliseconds. Okay, that's a requirement. That puts a requirement on W plus L plus E. So now you know how to design your network. You know what you have to check your software against, the thresholds that you have to check your software, and you know how much you need to spend on clock synchronization because you have this requirement that the database needs to respond within 30 milliseconds. So it makes this a very nice engineering framework. Moreover, the assumptions are clearly stated. You are forced to assert what your assumption is about your bounds on execution times, network latencies, and clock synchronization. So typically in embedded systems, these assumptions are not explicitly stated, but they're still there. And here you're actually forced to be explicit about them, which is going to make certifying the system far easier, because now you can get a separation of concerns. I state the assumption that under the assumption that the network latency is bounded by something, then the execution will be correct. And now I can separate the problem of assuring that the network latency is in fact bounded by that amount. That gives you a nice, separate separation of concerns, separate verifiability of the application software from the platform that implements it. Now, this model was not invented by Google, although it was independently reinvented by Google, and it was introduced by two people in my group. Yang Zhao was a PhD student in my group, and Jia Liu was a former PhD student with whom we were collaborating. And we published a paper using this technique for cyber-physical systems in 2007, and we called it Ptides with a silent P. So it has some cost, right? The synchronized clocks are the thing that many people immediately react to. This picture is from the Berkeley campus, and it shows two horribly unsynchronized clocks. But the fact is that synchronized clocks are becoming ubiquitous. I mean, when was the last time you had to set a clock on some device that you that you installed? It's becoming a routine part of the infrastructure. Cisco builds into all of their networking gear extremely high precision clock synchronization, and they use it to timestamp all of the logs in the network in order to do network forensics. Now, unfortunately, those synchronized clocks are not yet exposed to the APIs for people who are using this network infrastructure. I'm firmly convinced that that's going to change, that it's going to become routine for software developers to be able to assume that on local area networks, all clocks are synchronized within microseconds, and on global networks, they're all synchronized at least to millisecond precision. We already assume synchronization on the order of seconds because, across the network, NTP is very widely used, and that synchronizes clocks to a bit under a second with very high reliability. But a second is too much latency to add for this safe-to-process analysis for many applications. So we need to engineer the networks to give us better clock synchronization. And I see that coming independent of this application area. I think it's going to be something that we will be able to routinely rely on. Bounding the network latency is, of course, always problematic. But the issue here is that whenever you make an assumption about a system, first of all, there's no such thing as a physical system that always executes correctly, right? All we can have is a physical system that, if our assumptions are satisfied, executes correctly. And when we want to build a safety critical system, we still have to build in detection of violation of our assumptions. So in the case of Google Spanner, for example, violations are actually easily detected. They're trivially easily detected. If the Dallas data center has issued a reply that the seat is available, and it later receives a timestamp message reserving the seat that has an earlier timestamp, it knows one of its assumptions was violated. And what Spanner does is overlay on top of this a fault handling technique that is based on the transaction schema, which is a commonly used strategy in databases. So the issue here is that violations are faults. They're not part of the program semantics. They're faults, and you have to build in fault handling. And similarly, bounded execution times are something that in real-time systems we almost inevitably have to assume. In this case, it's only needed in particular places, and those are very well-defined parts of the software. So how are we working on this today? So the Ptides model was introduced in 2007, and about a year and a half ago, we started a project to develop a programming language that would be able to very cleanly define applications like this. And this language has developed into something that we call lingua franca, and you can download the current state of this. Here's the GitHub link for it. And an application sketch for this, and I'll just very quickly give you a sense of what the language looks like. So we have components that we call reactors. You can think of these as actors revisited. Like actors, they can receive messages. Unlike actors, they have explicit ports. So they share that, for example, with UML-RT, which has input, which also has ports. So these are named ports. So a reactor that performs a simple computation here, for example, would be written in lingua franca like this. It has an input named X with a type, an output named Y with a type. These inputs will be timestamped, and the outputs are logically instantaneous. So whenever a actor reacts to an input with a certain timestamp, any outputs that it produces will have the same timestamp as the input. This is a property that we borrowed from synchronous languages. And it's a very nice property because it enables a very strong form of determinism in the execution of the program. Reactors can have local state, and the reaction signature defines what the triggers are. So in particular, this says that the reaction will respond to an input on port X and will potentially produce an output on port Y. And this signature gives us dependency information, which we can use to analyze dependencies between reactions, which enables us to calculate the safe-to-process thresholds that are needed by Ptides. The body of the reaction is actually given in a target language, and we made a deliberate decision that lingua franca is a polyglot framework. It's a framework within which you build programs in your language. It's not a programming language. So we've built targets in C, C++, TypeScript, and Python. So you can put the body of your reaction code in any of these 4 languages today. And you can verify this, download from our GitHub repo and start writing your C code or your Python code in the body of the reaction. So the principle here that we're using is we use a model of computation where designing software that satisfies the properties of interest is easy. You build it like you were building a simulation of your system with this notion of logical time governing everything. The implementation of the model of computation, the framework, is verifiably correct under reasonable, clearly stated assumptions. So we have to clearly state our assumptions about network latency, our assumptions about bounds on execution times, and bounds on clock synchronization error. And then if those assumptions are satisfied, the execution of the program will match exactly what was specified in what looks like a simulation language. The hard part is 2, of course, where it should be, but this is done once for many applications. That's part of the framework. And so this follows the logic of keeping the hard stuff out of the application logic. I'll skip over the determinism property, but take my word for it. If the assumptions are satisfied, the entire distributed program is deterministic, which means that time-stamped inputs always produce the same time-stamped results. It's also possible to explicitly specify timing behavior, and it's possible to have event-triggered behavior even coming from asynchronous outside events. So this is required, for example, in Google Spanner, where you don't anticipate when queries are going to come into the database. So these are supported in the language, but I'll skip over that. There's some online resources to access more details if you're interested. We can also specify deadlines which relate this notion of logical time to physical time and are treated as fault handlers. So these deadline violations will lead to non-deterministic programs, but we treat them as fault handlers, not as part of the correct execution of a program. The status of this is it's still fairly early stage. The language is very much under development, but I'd like to emphasize that when we started this project, I was very worried about performance, because I thought discrete event, there's a good reason maybe that discrete event is only ever used in simulation and not in deployment. I'm astonished by the performance that we're getting. So just to give you a number here, for simple regression tests using the C target, on my laptop, I can get up to 28 million reactions per second, which is 36 nanoseconds per reaction. And it can make use of all 8 cores on my laptop simultaneously if there's enough parallelism in the application. So the performance that we're getting is very competitive, in fact, dramatically better than what you typically get from a discrete event simulator, and much better than many of the actor frameworks that are out there. The code size is also very small with the C target, so this can be deployed to embedded systems. So in conclusion, lingua franca programs are testable. You can write test vectors, which are the time-stamped inputs, and under the assumptions, if the assumptions are met, the correct behavior, the correct execution of the program will give you a deterministic set of time-stamped outputs. So that's a very nice feature. It enables regression testing. Lingua franca programs are deterministic under clearly stated assumptions. Violations of the assumptions are detectable at runtime. And actors, publish and subscribe frameworks, service-oriented architectures, and shared memory have none of these properties. Thank you very much.
Thank you very much, Edward. There are questions.